Previously, we've talked about the addition principle and the multiplication principle. We talked about factorial, we've talked about permutations, we talked about k-permutations. Now I'm going to show you the cousin of permutations, combinations. Namely, we're going to start off with talking about k-combinations. So we're going to talk about k-combinations first. So k-combination of a set. So we're going to let n and k be positive integers or potentially 0. So this is a fancy way of me saying, oh, positive integer or 0. That's a union in there where k is less than or equal to n. A k-combination of a set A I'll say finite set A of n elements is a subset. So it means it's if I were to look in my set, I take some of the elements and I put them aside. That's a subset. It could be even all of them, or maybe even none of them. Is a subset with k of the n elements. So a k combination would be some subset that is of size k, where it's k of the elements of the set A that consists of n elements. So let's do an example. Let's consider the example we've been using. Suppose that we're given a set A, which has elements A, B, and C in it, which has n is equal to 3, right? Because there's 3 elements in it. And for each 0 is less than or equal to k is less than or equal to n, we have as follows. So I'm going to show you how you would list out each one of these. So if you want to know what a k combination would be for a given k, it'd be somewhere in this listing of subsets. Just to be clear, they're subsets now. Now we do not care about the ordering. This is the one thing that's going to really separate permutations from combinations. Is like I talked about on side, I talked about the idea that suppose I go to the grocery store and I'm looking for some cheese. I want to get mozzarella, cheddar, and Gouda. In the world of permutations, I would care about which order I did receive those types of cheeses. In the combinations world, I would just care about that you got me the cheeses I was after. So I don't care about the order they appear in. It's just that they appear in that subset. So the order does not matter. So I'll just mention this off to the side. That's different from permutations. Order does not matter. So when k is 0, there's namely only one subset that you don't pick any elements from. It's namely the empty set. This is kind of like the parallel version of our permutations where we had the empty listing. So it's just 1. When k is 1, there are 3 k combinations, namely where you put one element each in a subset. So I have A, B, and C. These are 3 different subsets of A, each with one element in it. So I get to choose one element. How about 2? For 2, I can have AB together. I can have AC together, or I can have BC, right? So please take note that if I put CB, that's the exact same subset. Remember, in a set, we don't care about the order the elements are in. Then for k is equal to 3, this is when we have n, we have just A, B, and C. So please take note, the order does not matter. One interesting detail I am not going to go into in this discussion, But one thing I really want to point out to you is that there is a little bit of there is a symmetry from the smallest value of k to the largest value of k. Do you take note of that? It's very interesting. That is not a coincidence. That is actually a very special property that, should we explore more about combinations and how they operate for counts in relation to each other, we might explore this property in the future. So, the first thing I really want to point out to you, this is just a fun observation that I really want you to notice. It's just something I like to point out so you can pick it up and then put it back behind your ear as a piece of something to help you think about things in other ways in the future. Notice that all possible subsets of A are listed over here, right? So all the possible ways I can grab those elements and throw them in some bucket, including when I don't pick any, or if I take all of them, they're all in here. These are all the possible subsets of A. So if I go over each value of k over this range, and I determine the k combinations for each k, I end up with every possible subset of A. But if you take all of these and you perform a union operation on each one of these buckets, suppose if I listed out all of these and I take all of them, I throw them into one super bucket. This actually is what we call, so I'll say taken together. It forms the power set of A. The power set of A. That's just a fun aside. So just to be clear, the power set in this case would be the empty set A, B, C, A, B, A, C, B, C. We got B, C, and then we have A, B, C. Right, I got 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, good. So this would be the power set of that set A. So I'm getting very, very excited. It's also not a coincidence that that number looks like a power of, like if you count up how many elements are in the power set, it looks like a power of 2. It looks quite similar to a power of 2. That's not a coincidence either. So I got 1, 2, 3, 4, 5, 6, 7, 8, right? That shouldn't be very surprising if you think a little bit carefully about it, but I'll let you think about that, why this might look like a power of 2 of some kind, why it looks somewhat symmetric. These are all interesting combinatorial properties of these objects. So that is something we'll most certainly explore in the future if somebody is interested in this. So anyways, a very natural question, as we have been exploring so far in our discussion about combinatorics here, is how many k combinations that are there of a given set? So let's answer this question. So I've been really excited to talk to you about this. How many k combinations are there? So we're going to explore this now. I'm going to do another example that illustrates some of the things that are going on, so that hopefully you can be exposed to something that's relating k combinations with k permutations, because there's actually a close relationship between these two types of objects. A very close relationship. And in fact, how we're going to derive this answer. So let's revisit k permutations. Here, I'll say revisit k permutations. Here we select k elements from n elements. But we care about, I'll put that in quotation marks, we care about what is an intrinsic property of k-permutations is that these are orderings. The order of the choices. So when the element appears, we care about that. We care about it. We care about it when we talk about our k-permutations, right? Any one of these k-permutations, it's some ordering. That's the point I'm getting at. In k-combinations, we care about whether an element appears or not. Right? That's all we really care about with the k-combination, is we just care if the element appears or it doesn't appear. It's either going to appear or it doesn't appear, right? So let's do an example. I just really want to show you something rather. There's something I was just on top of my head. I was thinking this is fun. So as an example, let's consider this set: 1, 3, 5, and 7. All its 3 permutations are the following. So let me list them all out for you. So I got 1, 3, 5, 1, 3, 7, 1, 5, 7, 3, 5, 7. Then I'm going to now, let's write the next row, 1, 5, 3. And I must stress there's going to be something very special about how I list these. So please, while you're writing this down, please take note of how I'm doing it. So it might give you a hint of what I'm up to. I'm going to show you what I'm up to in a moment. So I have 1, 5, 3. The next row will have 3, 1, 5. And then I'm going to have 3, 5, 1. Then I'm going to have 5, 1, 3. And then lastly, I'm going to have 5, 3, 1. Second column, 1, 7, 3. So I'm just going to flip 3 and 7. Then I'm going to put 3 in the first spot. 3, 1, 7. Then I have 3, 7, 1. Then I'll put 7 in the first position. 7, 1, 3. Then I have 7, 3, 1. Next, let's do this next column. So I'm going to flip 5 and 7 to make 1, 7, 5. Then we have 5, 1, 7. Then I have 5, 7, 1. And then I'm going to put 7 in the front. 7, 7, 1, 5. And then finally, we're going to have 7, 5, 1. Final column. We have 3, 7, 5. I'm just swapping 5 and 7. Next, I'm going to put 5 into the lead. 5, 3, 7. Then I have 5, 7, 3. Then I'm going to put 7 in the leading position. I'm going to have 7, 3, 5. And then I'm going to have 7, 5, 3. I'll leave it to you as an exercise to double check that I've enumerated all 3 permutations of this set A. So there's something really fascinating going on with the way I've arranged this here. So this is arranged very specially. Does anybody see anything interesting going on over here? So this is a special arrangement that I've cooked up here for you. And in it is actually hiding the multiplication principle in the way I did it. So does anybody see anything fascinating going on here? So if I wanted the answer to how many k combinations there are, what are the k combinations of this set? Particularly, what are the 3 combinations of this set? Well, I pick 3 elements from this set. Remember, I don't care about what order they're in. But you can imagine each one of these ones I have on the top of each in this first row as a representative of the 3 combination for its respective 3 permutation. So notice that each column actually represents a 3 combination. And all of the 3 combinations, there's actually exactly how many? There's 4 of them. One for each column. And the elements in there are, you can take any of the 3 elements from any one of these in this column, and that's the first k combination, well, 3 combination. This is, so you can just look at the top of these, any one of these ones in one of each column. If you just pluck one of them off from one of the columns, it gives you one of the 3 combinations that are possible. So think about it like this. I want to know how many there are. And let me kind of make this a little bit more evident for you. I'm going to take you back to something cute about geometry. So I have a question for you. How many columns do I have? In this example, I have 4. But I really want to know how I get 4. Now, I want you to imagine that these are actually squares. So imagine I have rows, which are going to represent, this is the number of rows, which is the width. And then we have the number of columns. So this is the length. But what is if you think about this as a rectangle, if you're looking for the area, what would the area be of this rectangle? So now, you might ask, Dan, how did you come up with this listing, and how do I determine the missing side? Well, I can encourage you to think about how you derive the missing side from all the information we laid out, but I'm going to do it now directly using the what principle? The multiplication principle. So all we have to do is determine this. So what is that? But I want to show you now how I came up with that listing. And you'll see that it actually is just the multiplication principle. In other words, suppose we had a set L with all k combinations of set A. Just generally, because we're not talking about 3 combinations anymore. We're just going to talk about k combinations of set A, where the size of L, or cardinality of L, is the number of elements. In this case, this would be subsets. So these are subsets, the k combinations. So I'll say elements in L. So I want you to notice something. Notice that that the k-permutations of A is where we take each k combination in L and compute for each its permutations. Right? We compute all the permutations of that k combination. So notice that all it is actually a process as follows. Is I pick a k combination, then I compute the permutations of that. So that is, we choose a k combination of A. Then, to be more precise than I was, then choose some ordering. Some ordering for the k combination, which makes it into a, what kind of thing? A k permutation. So notice it's actually a process. It's two steps. Well, just remember observations. The number of k permutations in total is n factorial over n minus k factorial, correct? We derived this earlier, which, remember, this we write as p and k, this whole expression. 2, how many permutations are there of k objects? Just k factorial, right? Because remember, when I pick a k combination, that's just some set. I want to know the number of permutations of k elements. It's k factorial. So that will give us the key ingredients for what we need to do. So now do you see how I came up with this table I had over here? Do you see now? So all I did was I choose some k combination. That's a column. Then each row is me selecting some ordering for it. So all I did was I exhausted all of those selections for the first step, and then I exhausted all the selections for the second step. And that's actually how I made that table over there. So that's actually where it comes from. So now, in a beautiful fashion, we can use the multiplication principle. So by the multiplication principle, the size of L times k factorial, right? Because that's what it says. The first step, remember, the first step is that we choose a k combination. That's the size of L. That's how many ways we could pick that, right? Then we choose some ordering for it, which we know that the number of permutations is this. Remember, this right here is step 1. So this is action 1. Then we choose some ordering for the k combination. That's action 2. The first something and the second something. The first something, how many ways can I do that? Well, it's the number of k combinations, which that's what we denoted as L, is the set of all of those. Then I have k factorial. That is the number of ways you could select an ordering for the k or k combination. But what did we determine? Well, when you do this, as I said, once you assign an ordering to a k combination, that is a k permutation. That means that we're actually exhausting all the number of k permutations. So that's actually equal to p and k. Right? But we could simplify this a little further. This is n factorial over n minus k factorial. Now, akin to when we talked about the area of this rectangle, I could divide both sides by what? K factorial. And then I end up with L, the size of L on one side of this equation. And this is totally valid to do because our numbers always remain positive, right? It never is going to become 0. So I have now that the number of k combinations is equal to n factorial over k factorial times n minus k factorial. So I divided both sides of this equation by k factorial. And now we actually have something interesting going on here, because now we actually know how many k combinations there are. So this right here is the number of k combinations. And it's denoted like this. So this is often read as n choose k. Specifically, n choose k is now going to be equal to n factorial over k factorial times n minus k factorial. So this is read as n choose k. And some people refer to it as the choose function. Some also refer to it as something called the binomial coefficient, which I'm not going to be discussing here today, but it is a close relationship with this so-called choose function. Now, but yeah, no, this is how we can find out how, this is one way to derive how many k combinations there are of a set A. Pretty fascinating stuff, right? Let's do some examples. So notice that really the relationship between k permutations and k combinations is actually very close. Namely, it's just assigning and ordering to a k combination gives you a k permutation. So let's consider a couple of examples of using our understanding of k combinations. So imagine you have a team of 12 people. Let's not have a team. Let's have a group of 12 people. A group of 12 people to join a team of 5 people. Five people. How many possible teams? How many possible teams of 5 people can you have? Well, we have 12 people we could choose from, but we need to choose 5 of them for the team. Quite naturally. So what we do is we choose 5 people from 12, which is, because remember, we don't care about the order in which we pick them, right? So it means that we're talking about combinations, not permutations. We just care that we pick the people, not what order we pick them in. So we got 12, choose 5, which this is 12 factorial over 5 factorial times 12 minus 5 factorial. But what's this? Well, this is 12 times 11. So I'm going to show you that, yeah, a common trick is you just write out the factorial as long as you need it till you can cancel one of the terms in the denominator. 10 times 9 times 8 times 7 factorial. So I just write it up to where I get to the factorial there. It's a common trick. And I have 5 factorial times 7 factorial, right? Because 12 minus 5 is 7. So naturally, let's do some canceling. So 7, 7. Naturally as well, we should be able to get rid of some more stuff. Namely, we got 5. So we have 5 times 4 times 3 times 2 times 1. So I got 5 times 4. Okay. I got 5. Okay, we got 5, 4, 3, and we have 2. 1 doesn't really matter, right? So 5 times 2 is 10, right? And 4 times 3 is 12, correct? So we can actually just get rid of 5 factorial entirely if we eliminate 12 by canceling and 10. So we end up with 11 times 9 times 8, which this, I believe this should be correct. It should be 792. So I encourage you to check that calculation. Pretty nifty, right? So next, let's do another example. A very common case where you might run into this scenario is if you're encountering strings, especially if we're talking about computer science. So we've already seen an example where we try to place things in a sequence, such as with passwords when we were talking for a while back. So suppose we are given a bit string. So a bit string, to be clear, consists of zeros and ones. It's written in binary. So it consists of zeros and ones. So let's ask a question about based on how many bits I'm going to use. So a bit is just either a 0 or 1. So how many 8-bit strings? So I must stress that that is going to be a byte, because we have 8 bits. How many 8-bit strings have exactly 5 ones? I'll write 5 in full. I should be doing that anyways. 5 ones in it. Wow. Let's think about this. Okay, I have an 8-bit string. So that means I have 1, 2, 3, 4, 5, 6, 7, 8. I have 8 positions. Each one of them has a unique index, right? This is position 1. You can start at 0 if you wanted to. It doesn't matter. The point is that I have 8 positions. 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. I have 8 positions. So there are 8 positions. And the thing is, there's supposed to be exactly 5 ones in the string. Let's think about, so instead of thinking of it like, oh, well, this position could have a 1 or a 0 in it. This could have a 1 or a 0. This could have a 1 or a 0. Instead, what happens is you pick 5 positions. What do you know about the other positions? If you put a 1 in 5 of the positions, it means all the other ones are going to have zeros in them, correct? So pick 5 positions and all the rest have zeros. But the thing is, we're making choices based on the set of positions. So this is why I really want to show this example, is sometimes it doesn't look like that we're really making a choice here, but it just really is thinking a little bit more carefully about what are we choosing over. In this case, it's not just a team, it is actually the positions in the string. So carefully conceiving what exactly you're counting over is actually a key element for some cases like this. This is a very helpful example in that regard. So we have a set of positions, capital P. We're just going to have 1, 2, 3, 4, 5, 6, 7, 8. For which we select 5 elements from P, right? 5 elements in P correspond to 5 positions in the string. Those are going to occupy ones. Which has the total possible count of what is it? What's going to go in my choose here? So what are my choices? I'm going to have 8 positions, so I have 8. Choose what? 5. 8 choose 5. 8 factorial over 5 factorial times 8 minus 5 factorial, which this is 8 times 7 times 6 times 5 factorial. And I have a 5 factorial that I'm going to attempt to cancel with. And then I have the 3 factorial, which fortunately I also can cancel out quite nicely. So the 5 factorial could go out with this 5 factorial. And then I have, what else? Well, 6 right here is just 2 times 3, right? Which is the same as 2 times 3 times 1. Which that is just simply 3 factorial. So I end up with 8 times 7, which that is exactly 56. Completing our example. So if somebody asks you, how many 8-bit strings have exactly 5 ones in them? The answer is 56. So that's all I have to say about k combinations specifically. There's other kinds that we're going to be discussing here shortly.